Greetings and welcome to Build a Neural Network in only 7 lines of code. You can do this in any language. All we need is basic arithmetic and loops. There's nothing fancy here. We're going for simple. That is our goal. We're going to create the simplest neural network possible. Why? Because it'll be easy to understand, easy to watch how it's working, and easy to see the impact of experiments. What is a neural network? Neural networks solve a function, but function can have many meanings based on context, so we need to agree upon a definition. For the sake of this video, we're going to say a function accepts inputs and produces outputs. So for example, you could have an add function that accepts a 2 and a 3 and outputs a 5. That's pretty easy. But now let's look at a real head scratcher, converting apples into orange slices. This isn't just difficult, this is the stuff of agricultural nightmares. If you can program this one in 7 lines of code, you're not just a programmer, you're a fruit bending wizard. But because it takes input, apples, and produces output, orange slices, despite being difficult, it is in fact a function. But that's where neural networks shine. And when you take that neural network and put it with training data, it creates a function machine, regardless of the difficulty. So for add, for square root, I don't need a neural network for that. But if I want to change apples into orange slices, that's going to be a bit trickier. The first neural network was called the Perceptron, invented back in the 1950s. To this day, it was considered the simplest architecture. However, I am introducing what I believe is simpler. So the way this thing worked is it had an input layer where you'd have data such as credit score, age, income, and years on the job. All those would go in and produce an output, a binary classification, yes, no, true, false, or so forth. So these might predict if somebody would pay a loan or not. But we want simpler. We're going to have a single input, a single neuron, a single weight, so there's no summing. We're going to have a single function, no bias, and hell no, we don't want any gradient descent. We're also going to start with super simple training data, and then once we got that working, we'll move to some more interesting data. We take the input times the weight, and if that is greater than zero point 0.5, we return a 1, otherwise a 0. What's the cost of being simple? When I started this quest to build the simplest neural network, I thought simple would cost accuracy, but actually I was wrong. It's highly accurate as long as your data is what's known as linear separable. And what that means is you can draw a straight line that separates the yeses from the nos. Now you can have a few outliers. What is training data? That's where you have data on both sides of the machine. You've got the apples and the oranges, the question and the answer, the input and the output. So, for example, you could have a bunch of old credit applications where you know what the result was. Was it paid off? You could use those to train a neural network to predict loans. You could have emails where somebody identifies if it's spam or not, and you could use those to train a neural network to be a spam filter. You could do the same to create an AI doctor, and you could have images like a kitten, puppy, lizard, and if the output of that was labels, then you could take those pictures and labels, feed them into a neural network, and that's how they do image recognition. But again, we want simple. So we're going to start out with two things, a credit score and a loan outcome. And to make it even simpler, the credit score can only be two values. One means good credit, 0 means bad credit. The loan outcome, same two values. One means they paid it off, 0 means they defaulted on the loan. Here again, we have good, paid, bad, didn't pay. Oh, but look at this one. This is an anomaly. Bad credit, but they paid it off. Maybe they just got a new job or won the lotto, who knows? But it's important to account for these, so we're going to include anomalies in our test data. Now, how do you use the training data to train the neural network? It's really easy, 3 simple steps. You guess. The guess, again, we're going to go back to that formula. Input times weight, is it greater than 0.5? Does it match the result? If not, update the weight. It's that simple. Now, this looks a little busy and complicated, but if you look at it for a moment, I think you'll agree this too is actually pretty simple because it's simply, here's our training data that we just had, right? Good credit, paid it off, bad credit didn't, repeat, repeat in our anomaly. We're going to start with a neuron weight of 0.8, and really you can put the neuron weight anywhere you want because what will happen is while you train the data, it'll adjust that to be what it needs to be regardless of where you put it. So let's look at what happens with 0.8. We take our input and the weight, so that's 1 times 0.8. which is 0.8. Is that greater than 0.5? Yes, it is. So we predict they pay it off, which is correct. They did pay it off. Because we got it correct, there's no loss, which is simply how far off was it. And because there's no loss, there's no tweak. We got it right. Let's look at the next one. Bad credit didn't pay it. We take 0 times our neuron weight, which did not change, 0.8. Is that greater than 0.5? Nope, that 0 is not greater than 0.5, so we predict they didn't pay it. And that is also correct. Again, no loss, nothing to tweak. Our weight remains unchanged. Just repeats the same thing for good credit paid it. Repeats the same thing for bad credit didn't pay it. But then look at our anomaly, what happens. In our anomaly, the input's a 0, the weight's 0.8. So we say 0 times 0.8. Is that greater than 0.5? No, it's not. So we predict they won't pay it off. But we were wrong. They did pay it off. But is it really wrong? Really, if the credit is bad, the best prediction is probably that they won't pay it off, even though sometimes there's anomalies. Any good poker player will tell you you need to get your money in when the odds are in your favor. Sometimes you get a bad beat and it won't pay off, but more often than not it would. So even though we predicted it wrong, I think we actually did make the prediction that was the correct prediction to make. You might be looking at this and say, well, that's well and good, Chris, but nothing's going on here. Nothing's changing until we hit the anomaly. What does that prove? Let's try a different weight of zero point 0.2 to start. So, input score of 1, good credit, paid it. Weight's 0 0.2, 1 times 0.2. Is that greater than 0.5? No, it's not. So we predict they won't pay it off. But that's wrong. Now here's the magic. So we take the actual value 1 minus our prediction, 0, and that says we have a loss of 1. So then we take that times the learning weight, and we adjust our weight by that much. So 1 times 0.1 is 0.1. We had a weight of 0.2. Now we nudge it up to 0.3. Let's look at this next example. Bad credit defaulted. So our new weight is 0.3. We take 0 times 0.3. Is that greater than 0.5? No, it's not. So we predict 0, which was correct. So in this case, no loss, no need to tweak. It stays the same. When we get to the good one, same thing happens again. And just like we had to raise it from 0.2 to 0.3 here, we have to raise it to 0.4 here. Now what's interesting about this is it's moving that weight to try and find that line that makes the data linear separable. If we go back and look at this one, maybe our 0.2 was down here. Each time it sees a good loan that was paid off, but we predict it wasn't, it's moving that line a little bit this way, a little bit this way, a little bit this way. And what will eventually happen is that line will wind up somewhere in between these. When I started, I thought it would be right smack dab in the middle, but nope. Once it finds a good line, it could be right on the edge of the reds, right on the edge of the blues, or anywhere in the middle. Once it finds that line, it says, I'm done. This line works. Nothing else needed. As you can see, the weights keep going up. But if you look at our results here, they don't look that great. 2 wrong, and then our anomaly again. Well, the answer to that is what's called epochs. Epochs is just simply repeating the training process with the same data multiple times. Let's jump to our code and look at how epochs work in our actual code here. So line 4 here has got our actual training data. Good credit paid it, bad credit did not pay it, good credit again, bad credit again, and our anomaly. Here's where the actual neural network starts. We set our initial weight to 0.2, and then here's where we actually bring epochs into the picture. This line 11 says run the below code block 5 times. Each one is an epoch. The below code block says, hey, for all of our data, however much we have, 2, 5, 10, run the below code block, and each time pull out the credit score and the result. So then we make our prediction, which equals 1 if the credit score times the weight is greater than or equal to 0.5. Otherwise, we predict a 0. Our loss, just like in the spreadsheet, result minus prediction. And then if we do have any loss, the weight is adjusted by it, loss times 0.1. If we don't have any loss, 0 times 0.1 makes that adjustment not occur. And then we print out the details. So let's take a look at how that looks. All right, so we ran 5 epochs here, and our first epoch, and notice it's printing the weight after we make the adjustment here. So in the first one it runs it, it's got good credit score, and they paid it off. But because our weight is just zero point 0.2, we predict 0, and that's not correct. So there is a loss, and that loss bumps the weight up to 0.3. We got it wrong, though. On the next one, it is bad credit, and they didn't pay it, which we do predict correctly, so nothing changes there. Then we get to another good credit, and again, we get it wrong, but we do move the weight up. Bad credit, and our anomaly, which is also wrong. So if you look here in our first epoch, we got 3 wrong, 2 right. Not so great. But notice how that weight is moving up. So our first epoch, 3 wrong. But if you look, by the time we get to the third epoch, it's correct all the way down until we get to our anomaly. And then it will be that way forever. That's how it works using our simplest data. But you might say, hey, that's kind of silly data. Great, you got 80%, but what if we were using more realistic data? What we're going to do now, we have a random process that basically says a credit score is from 1 to 100. Let's say it's 75. That's the probability that they'll pay that loan off. So at once we've set the credit score at 75, we roll the dice again with a 3/4 chance they paid it off and a 1/4 chance they didn't pay it off. By generating our data that way, it will be linear separable. So here's the data that it generated randomly. 44, which is right, anything less than 50, we'll say, is bad credit. So 44 didn't pay as expected. 65 did pay. Oh, but here's an anomaly. 28, bad credit, but they did pay it. And notice, they're really pretty good, especially factoring in that some of these wrongs are probably anomalies where we made the correct prediction, but it was just unlucky, like that bad hand of poker. We have a function that generates random linear data. It'll generate however many we want, and we can tell it to include anomalies or not. So down here, when this actually runs, we say include anomaly, give me 30 pieces of data. So we do have some wrong, but you can see we mostly have correct by the time we're into this fifth epoch, but still quite a few wrong. Well, why is that? It's because of the anomalies. Look at this. If we take the anomalies and we say false here, don't include any anomalies. So that means if it's 50 or greater, it'll say they paid it off. And if it's 51 or 49 or lower, it'll say it defaulted. And when we run that one, you'll notice by the time we get to that fifth epoch, it is 100% correct. So the trick, what we're going to have to do is figure out how do we take these 7 lines of code, which is simple, and improve it so that it handles these anomalies better. Because in the real world, the data won't be perfectly linear. That is a neural network in 7 lines of code. But it was kind of hard to see what's going on when all you have is this detailed look. So in our next video, we'll talk about the neural network arena. And what this lets you do is create slightly different or very different versions of the neural network, create one set of training data, and then run that data through each of the contestants, so to speak, see how they all do. As you can see, just a plain Simpletron is getting about, well, 2/3 correct of accuracy. When you put in gradient descent, it drops about 10%, which is about average. Every now and then gradient descent will be higher, but very rare. And then you can do as many of these as you want and run them together. So if you don't want to miss that video, please subscribe. If you enjoyed the video, I'd sure appreciate a like, and I'd love to hear your comments. I will definitely read and reply to them. So please let me know what you think. Thank you so much for your attention, and have a wonderful day.